Alright, so you should be about the same spot as what I have up here. I left most of the notes from yesterday of what you can read. So we have arctan of 3/4. We were trying to find the error or the remainder here. The error bound we were given was 1/10, so we wanted to find that next term that would be less than 1/10. Again, thinking about the alternating series. When we had the alternating series and we found that error, or the remainder, we found that next term that we didn't use that was less than the error bound that we were talking about. So we were up to the point where we found the third term, and the third term was 0.047. That third term, that's less than 1/10, so that's that term that we were looking for. So we know if we add these first two terms up, the error of these first two terms has to be less than 1/10, because the total of our third term is less than 1/10. So the error has to be less than 1/10. Okay, so that was the idea that we were getting at yesterday. So we're saying that this A here, we're only going to use these two because we're not worried about the one that's less than 1/10. So 3/4 minus 9/64. And if you got common denominators, found your answer, you'd get 39/64. So this is what A is. Again, we found those terms until we found one less than 1/10. Do not include that one in your A term.
Would this one be a calculator one?
It is not. I threw in the decimals here for you, how you would do this. 3/4, you know what that is, 0.75. 9/64, you would have to reason and try to figure out what if it was greater than or lower than 1/10. And then with the 243, 5/5120, you could set that, this part here, you could take 243 over 5,120 and set that equal to 1/10 and get a common denominator. Or actually, you want that to be less than 1/10. Common denominator, multiply that by 512. So you get 512 over 5,120. So is 512 over 5,120 greater than 243 over 5,120? Yes, that's what we wanted. And that's how you could check each of those if they say non-calculator. Just make it less than your remainder, find a common denominator. Okay. But I just simplified the problem a little bit and threw in the decimals, yeah.
I have a lot of questions. Like, how did you know that we're supposed to solve for the error? Like, I'm really confused. How do you know to solve for the error? Like, I put it in my calculator and that A value works, but like, what if I arrived at a different A value? Like, by a different approach? There's
What do you mean by a different approach or finding a different?
Well, like, what if I just did it algebraically?
How would you do it algebraically?
Just like solve for the arctan of 3/4 using the series found in part C, and then like just use algebra to solve for that once I have a value for that.
Did you do it that way?
Well,
Since
no,
you're asking the question, I just wondered if you did get a different A value.
I thought we were going to, so I started, and then started doing something about error, and then I got lost. How did you know that we were supposed to find error? And like, I don't know. I have a lot of questions.
Well, the reason that we knew we were going towards the error is we recognized a pattern like the alternating series test in this one, where we had plus, minus, plus, minus. We know we had that error bound with an alternating series. Again, we mentioned yesterday, integral test and alternating series were the only two we ever did some kind of error bound with. The alternating series test is going to be the important one. You're not going to use the integral test one as much. So the alternating series test is the one that you need to use. And we realized it had a similar pattern to that. Yesterday I had these labeled. I erased them here. But we had approximate minus actual had to be less than this error bound. So the whole setup was very similar to what we had with alternating series. So that's why we went towards this error bound. And we know that this whole thing here is going to be the error or the remainder left over. And again, this was used from up above, the arctan. Yeah, we had the arctan already from up above, just plugging in the 3/4. So that's how we found these values here, plugging in from up above. Now, we're not done yet. I haven't stated the final answer yet, so do we want to go ahead with that and see if this...
Oh, so A isn't... 39.
This isn't our final answer yet. That's not our final answer yet. No, this is just saying what A is. So we're saying now...
Find the rational number A?
It is, but they want to justify your answer.
Okay.
So we had the absolute value. Actually, I'm just going to write it up here so I have more room. The absolute value of A minus arctan of 3/4 less than 1/10. Again, that's what we were using. And our justification is we found that 243 over 5,120, again, that's that number from right here, was less than 1/10. So now again, we used alternating series, that's what we were referring to. So our conclusion, the series is converging and alternating with terms that do what? Again, with the alternating series, what did those terms have to do? They did have to alternate. They had to do two other things. Decrease is one of them. Decrease to what? They had to decrease to 0. So what we had done there, we found that part in this series that was less than our error bound. So again, just like the alternating series, we know that that term, whether it's added or subtracted, it's less than 1/10. So we know every term added up before that, that sum has to be within the error of 1/10. So this is the A value, the actual value that we have. This is the actual value that we have, A, minus this arctan of 3/4, or the approximate, sorry, minus the actual, would give us some error that's less than 1/10. Okay? Does that help anything, Eric?
Yeah.
No?
Can you explain that? Okay,
I'm still really...
so we found, okay, sorry, the terms up until it was less than 1/10.
Yeah, this was the first term that was less than 1/10.
Okay.
Again, same, relating back to the alternating series, that's what we did. They gave us some error bound, and we went up until we found that first term that was less than that error bound they gave us. This one's less than it. So we know if we add, or in this case, we have subtraction here because it's alternating series, adding or subtracting them, that value that we get, the error within that term has to be less than 1/10 because we know the next term is less than 1/10, and with alternating series, as we go on, each term is decreasing, getting closer and closer to 0.
Okay.
So we know that it has to be within 1/10 of this value.
Okay. What exactly is that A value? That's like...
This would be our approximate value of arctan of 3/4. This is our approximate because, again, there's some kind of error there. Yes,
That's as
it's close.
to the value that's less than 1.
Yes, we know this value here has some error, but that error is less than 1/10.
Okay.
So this is the close approximate that we have of arctan of 3/4 right now. Does that help out a little more?
So, yeah, I think I understand, like, why you did it
We're
that way.
trying to
Why couldn't
approximate
I do
that.
it another way? Why couldn't I do it, like, where I just do it algebraically?
It might be possible. I'm not sure. That's something we could work out and see if it...
So it sounds a lot easier.
But there's definitely going to be problems with this reasoning, again, that you're going to have to apply to problems where you're not going to be able to solve the way that you want to now. So having the idea with a more simple problem will apply to more sophisticated problems down the road. Again, and this is this example here is leading us to the next section that we're going to look at today, 3.6, Lagrange error bound. It's going to be a whole section just on finding error bounds. Okay? So this is really leading us into that next section, knowing the idea of being able to find something that's approximated very closely using some error bound that we're given. Deep thought, Eric?
Yeah, I thought I understood it when I was done. I'm looking back over it now, I'm like, I'm just going to have to take a look
Essentially,
back at that. I
the
think I
top
understand
part.
what's going on.
Excuse me, finals first place. Can you please explain this stuff?
Yeah, did you have something to say, Caleb?
No, the top part says like the series is convergent, like essentially it's always gonna, aren't you always gonna be able to find a value that's less, or like it,
So,
you know,
this one's less than 1/10. If we find the next one, is it also going to be less than 1/10? Yes, because they're decreasing and going towards 0. So yes, the more terms you add, the closer this a value is going to get. But they just told you to find the a value and less than 1/10. Well, we came to the first one. Again, we're doing this by hand and without a calculator. We found the first term that's less than 1/10. Well, that's all the work I'm going to do. I don't want to go any further. I'm not using a calculator. I know it's less than 1/10 here, and that's all they're asking for. If I go further, yes, I can guarantee for sure it's less than 1/10. But this is the first term that guarantees that error is less than 1/10.
okay.
So yes, the further you go, the closer this approximate, gets closer and closer each time. Again, that's what we did with the alternating series before. Okay, so you are exactly correct with that. Are we okay to move on? Do we want to talk a little more about it? What? We can always go back to it too if we think of something else, okay? If you come up with another question, we can go back to it, Eric. Okay?
Give me another question.
All right, on the back. So the back is a little change of gears for a moment. We'll get back to the error bound in the next section. But with example 13, we need to think back to those series that we have memorized on your note cards. So we're going to use those and manipulate those to try to find sums. So it says, besides finding the sum of an infinite convergent geometric series and the telescoping series, there's one last way we are expected to find such sums. By recognizing a given infinite convergent series as a Taylor series evaluated at a particular value of x. Again, those ones you have on the note cards, that's what they're saying there, the ones we have memorized. By recognizing each series as a Taylor series evaluated at a particular value of x, find the sum of each of the following infinite convergent series. So let's just focus on letter A. Of the ones thinking back that we've dealt with, what kind of pattern does this meet? What kind of Taylor series do you think that resembles that we could use?
Cosine.
Yes, it does resemble cosine. So if you think about cosine when we had that was of this form, but instead of pi's, we had x's here. So what we're actually saying is we're evaluating the Taylor series of cosine at x equals pi. So cosine of x at x equals pi. Cosine of x at x equals pi. So that's cosine of pi. What is cosine of pi? -1. So the sum is equal to -1. And that's it. So being able to recognize this pattern, because we had cosine memorized, we use the pattern and we know if this pattern, if we plug in pi, the answer is -1. That's why recognizing these patterns could really be helpful. Again, you don't have to go in your calculator then and type out a bunch of terms and see what it's coming close to. You know because of the pattern, -1. Go ahead. What was that?
So why do we take cosine of pi? That's the rule that.
Well, we know this represented cosine of x. That's what we had memorized. So the cosine of x pattern, instead of these pi's, we had x's. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Again, we noticed it's even powers, 2, 4, 6. It's over 2 factorial, 4 factorial, 6 factorial. it's alternating. Those are all the characteristics of the cosine.
Okay. And then there's point and pi.
But instead of x's, there's pi there. So again, we know this is cosine, but instead of cosine x, it's cosine of pi. Well, cosine of pi, we know what cosine of pi is. That's -1. Okay, Caitlin?
Yeah.
All right. Let's try letter B. What kind of pattern does this fit? What do you think it resembles? We notice that it's all addition. We have some factorials. We have powers there. What does this resemble? Well, it would represent a Maclaurin series because the center has to be at 0 here.
But it's like Maclaurin with the N squared or
So think about, we have 1 here. Normally we would have 1 plus what? What would be the next term? X. So think about ln of 4 as x. And this would be x, x, x. So what does it represent? Not sure if I heard you, if you said it, Eric, or not. Well, it is Maclaurin, but what function does it? Yes, that's what. It represents e to the x. So e to the x evaluated at ln of 4. So again, we know this represents e to the x, so it represents e to the ln of 4. Well, what does e to the ln of 4 equal? 4. So the sum is equal to 4.
I like these ones.
I do too. And the more you have the other ones memorized, the quicker these ones go, and you don't really have to think about these ones as much. Okay, over there, Autumn, you look confused.
I'm looking at the next slide.
Okay.
That's why I'm confused.
All right. So let's go ahead and look at the next one. It does have a little more going on. The first thing I would recommend looking at is look at your signs, because that can help you determine if you have them memorized. You know, some of them are all addition, some of them alternate. So look at your signs. Well, we see this one alternates, so then in your head you can kind of eliminate a few of them. You know, like, for example, it can't be e to the x because they're all addition. Which ones alternate? What could this be? Well, cosine alternates, but cosine we used up above starts with 1. This one doesn't start with 1, so what could this be? Some form of sine x. So, if we have pi over 6 representing our x, what else is different about this one? We have x. Yeah, it also needs multiplied by 2, because we have a 2 in front of each term. So 2 sine x, evaluated at x equals pi over 6. So 2 sine pi over 6, 2 times what? What is sine of pi over 6? Think about your unit circle. No, not quite. 1/2. Yep. So 2 times 1/2 is 1. So the sum equals 1.
You just gotta pick one. He says close to negative.
Do we like these ones better? So again, these ones are easy as long as you do have those memorized. So again, try to figure out what x would be. We found pi, ln of 4, pi over 6, those were x's. And that third one, see there, do you see where we came up with that then? Like your confusion on that one is better now? You're good? Okay.
I just saw the 7 and I was like, I don't remember seeing the 7 in any.
Yeah, another thing to recognize in this one I forgot to even mention, and she brought it up with the factorials and the exponents there. Again, these are all odds. So this first one was even. We know cosine is an even function, sine's odd. So again, that's another one that can really give it to you. You know it's alternating and it's odd. Well, then we really have to be going towards sine. Okay. So those are some things to think of, again, especially when looking over your note cards. All right. So this wraps up section 3.5 for the geometric series here. So we're really going to move into 3.6. It'll be the last section of this unit. We might be able to finish 3.6 by Friday. We're going to see how it goes. We're not going to get far into it today, but I just want to give you an introduction to it, and then we'll call it a day. Alright, so 3.6 is what is known as Lagrange error bound. This is also known as Lagrange form of the remainder or Taylor's theorem remainder, so those are different ways that it can be stated. Most often, when you're asked a question, it's going to ask, find the Lagrange error bound of the problem, okay? So that's what it's most often referred to as. We're going to have a few different examples here of, so suppose you didn't have a calculator, but you wanted to find the value of sine of 1. How could you approximate its values? Well, we have some examples listed there, but think about different ways in the past that you found it. One way is the tangent line. If you draw the sine function, you could draw a tangent line and approximate the value of sine of 1. You would center, where would you want to center that approximation or draw that tangent line? If you think about a sine function, where is it going to originate? At 0, yeah. So you have a tangent line approximation, your center would be at 0 there. That's going to get it close. They have a few others. You could eyeball it on the graph, so you could graph it and then look close to where 1 would be and get an approximation of it. You could think of sine of pi over 3 and know that it was some value close to square root of 3 over 2. So just some different methods. Euler's method, drawing a bunch of different tangent lines, approximating it closer. Or what we most recently have done, the Taylor polynomial of degree greater than 1. Again, if it's a Taylor polynomial of degree 1, that's a tangent line. So that's why they say degree greater than 1. That's when we started approximating the curves, the last two sections that we've been dealing with. So suppose we choose the third or fifth option. After all, polynomials are relatively easy to evaluate. Is there a way, depending on the degree of the polynomial we decide to use, to determine how accurate our approximation is? That is, do we know the remains from our approximation to get the actual value? And it says yes, yes we do, kind of. So this is where Eric has questions. All right, so moving forward, the rest of this page here is really just going to be our setup of what we're going to be using with the problems. Okay, so we're going to have a Taylor polynomial. The T of n is going to represent a Taylor polynomial of degree n, centered at some x equals c, used to approximate a function f of x at a value of x equals a. So again, we're trying to evaluate at some specific value. We want to approximate at that value x equals a, near the center. So this is how you would express your results. So our function, if you think about a function evaluated at some value, this would be your actual. So if you evaluate a function, that's your actual value of the function. A Taylor polynomial. So like what we've done in the past section or two, Taylor or polynomial approximation. This would be your approximation, just like our Taylor polynomial. So it says polynomial approximation. You don't have to write approximation if you don't want to, but represents like the Taylor polynomial that we have been dealing with. Plus a remainder. The remainder is also known as the error. That's what we had also found with the alternating series and that example we had in 3.5. The remainder is also known as the error. So if the function, the actual, is equal to the approximation plus the error, then the remainder, or the error, is equal to the function, the actual, minus the approximation. So again, in terms of how we used it in previous sections, you would take the absolute value of the actual minus the approximation. That's what we had done in the last couple sections. Now you could just leave it as actual minus approximation and not use the absolute value, that's going to give you a negative sign. That can help you figure out whether your approximation is greater or less than. But normally we take the absolute value of it and just say the remainder is this, the absolute value of those values. So that's how it is written in words. So mathematically, in the terms we're going to use, again, some function evaluated at A, that's a restatement from up above, that's your actual, is equal to this Taylor polynomial. Again, we've been dealing with the Taylor polynomials, evaluated at some A, plus the remainder or the error at that value A. But again, what we're looking for that remainder or the error. So the remainder or the error, solving for that, is equal to your function evaluated at that value of A, so that's your actual, minus, they had P for polynomial function, you can put T for your Taylor polynomial function. That way you keep it consistent. T, that's your Taylor polynomial function. And at the bottom, this is what really brings the idea together. So this is using Taylor series, and this is what Lagrange had found for the error bound. So again, we're looking for that remainder of the error bound at the specific point A. And we stated up above, that's your Taylor polynomial subtracted from your, or subtract your original, your actual function, absolute value. So that's what we mentioned up above. But the derivation we don't actually have here, but this is what the derivation is, so that's something you can look up if you want to see how this is actually found, the Lagrange error bound. But we're going to say multiple things about this because there's similarities to the Taylor series with this. We can see the Taylor series was f to the n of the center over n factorial. Again, when we were doing Taylor series, that's how we found all of our coefficients. So this is similar. This is the nth plus 1 derivative instead of the nth derivative. We have some term z here. So that z, we're going to talk more about that. We don't actually know what that value z is. And then a, this is the value that we're plugging in, some x equal to a. So this will be plugged in instead of being left as an x, like in the Taylor series. We're actually plugging in some a there. What we do know about z, though, z is an x value on the interval from x comma c, so whatever x value we're trying to approximate to the center. And you can write it either direction because, again, because of that error bound, it can be added or subtracted. So it could be c to x. So some value x is what we're trying to approximate, and we know this z value is something on the interval from x to our center. But what's important about this, again, thinking back to that problem we had in the last section, that error was 1/10 there. That's the maximum error we could have. So we're trying to find this value z within this interval that maximizes f of n plus 1. Trying to find something that maximizes that. Again, if we take that value that's maximized, we know our error has to be less than that value. So that's why we're trying to find the maximum value within that interval. Because if we just use any value within that interval, we're not guaranteed to be under that error bound. Okay? So kind of like with that example in the last section, we had to find that first one that was less than 1/10 because we know if it was less than 1/10, our error had to be less than 1/10 for those terms previously added together. So that's what we're doing for this the f of n plus 1 derivative here. We're trying to find the upper bound for that. We're trying to find out where it's maximized. So I think once you actually see an example of this, which is the back side of this page. The whole page is going to be one example of actually finding this error bound. I think it's going to make a lot more sense, but I don't want to jump into the example and just get halfway through it, so we will start with the example tomorrow. Okay.